It's a pleasure to introduce Huanhuan Li, who's our speaker today. She will speak about graded and filtered K-theories for Leavitt passages. Please, Huanhuan, go ahead.
Thanks, Willy. And first, I thanks Willy for the invitation to give the talk, and thanks all the organizers for this global non-commutative geometry seminar. So for my talk, it will contain the following several parts. The first part, I will introduce the definition of a Leavitt path algebras for direct graphs, and we will also see some simple examples. And for the second part, I will talk about the graded graph monoids and the cross-antic groups for Leavitt path algebras. And for the third part, we will talk about a sort exact sequence of cross-antic groups for Leavitt path algebras. And the fourth part is about the filtered K-theory for Leavitt path algebras. And then for the last part, we will have our main result. So actually for the first, we recall the Leavitt algebra, so which actually was introduced by Leavitt in '62. So this algebra, it's the free associated algebra A over a field K generated by xi, yi. So I is from 1 to n, and subject to the following two relations. The first one is the xi, yj is third ij, and the second relation is the sum for yi, xi is 1. Actually, using these two relations here, one can construct the following two maps. So actually, so let's see, the first map phi, it sends A to this vector. So that is multiplied by the xi's from left-hand side. So we can see this is a right model homomorphism, a right A model homomorphism. And we can also define psi. So it starts from an to A, and we use the yi's, and we can give this map. And actually, phi and psi, they are quasi-inverse for each other. And we are using these two relations, we can see that. And that means this algebra, it has very special property. That means the model, the regular model A is isomorphic to AN. This is called the algebra of type 1N. And for algebras, they studied also C-star algebras. Actually, it's maybe around 80. So the C-star algebras, they consider the Queen's C-star algebras and Queen's-Krieger C-star algebras, and also graph C-star algebras. Actually, Morano Pardo and Abrams Radapeno, they introduced the Leavitt path algebra in the year around 2005. So actually, they introduced it independently. So actually for the Leavitt path algebras are the algebra version for the graph C-star algebras. So for Leavitt path algebras, basically we can see we can view this as we have a functor like this. So we start from direct graphs, and then we have associated algebras on the right-hand side here. So it's like giving us a graph. For example, this rows with n petals. then we can actually have a, we use the graph data, then we can have a Leavitt path algebra. So we denote by L1n. Actually, this L1n is it has the following two relations. So this is exactly the Leavitt algebra we introduced at the very beginning. So that means this Leavitt algebra is a very special Leavitt path algebra. So actually, for the definition for Leavitt path algebra, it's like this. So we write E as our graph, and the K is a field. So we define the Leavitt path algebra of a E over the field K to be the free associative K algebra generated by the following set. So the first set is the vertex set for the graph E. So this is E0. So this is vertex set. And the second set is the edge set for the graph E. And also we have for each edge in E1, so we have a symbol we denoted by alpha star. So this we call star edges. So these are the generators, and we also need to have the following relations. So the first one, I mean that the vertex is actually they are idempotents and they are orthogonal. So that means for different vertices, the multiplication is 0. And for the second relation is for any edge in the graph E, so say alpha, we have the starting point of alpha multiply alpha should be equal to alpha. And similarly, we have the multiplication for alpha with the range of alpha is also equal to alpha. And for the star edges, actually, we think the star edge is like an opposite edge of the original edge alpha. So it has the relation that the range of alpha, so we have the multiplication for the range of alpha, and the alpha star is alpha star, and the multiplication for alpha star with the source of alpha is alpha star. Okay, let's see the third relation. That's for any two edges, alpha, alpha prime, we have alpha star, alpha prime is the delta alpha, alpha prime range alpha. And the last relation is for any vertex in E0, which is which has edges starting from it, and they are exactly only find many edges starting at it. We can have this. We have this relation that the sum for alpha alpha star is V. So here the sum is for all these found many edges alpha starting from V. So here this Leavitt algebra we denote by LKE. So sometimes we just simply denote it by LE. So in our case, we always assume our Leavitt path algebra is over a field K. So actually, we can give a Leavitt path algebra a natural Z gradient by setting the vertices to be degree 0 and the edges to be degree 1 and the star edges to be degree -1. So then in this way, that means the Leavitt path algebra is Z graded. So let's see some very simple examples. So suppose first we have this graph E1, which has only one vertex and one loop. Then the Leavitt passage for this graph actually is Laurent polynomial ring Kx inverse. So we can see from the relations of Leavitt passage that actually for the alpha here, for this loop, if it's alpha, then alpha star is 1 and alpha star alpha is also 1. For the second graph, so suppose we have E2 has 3 vertices and 2 edges. Then this Leavitt passage is actually a matrix string. So we can send the vertices to the elementary units for this matrix, and we send alpha to E1, 2 and beta to E2, 3. And so on. Here we have also the star is for this. So we can see that this is an isomorphism of algebras. And for the ninth graph, it has 1 loop and there's 1 edge starting from the first vertex also. So actually, we can first construct an algebra homomorphism from the free key algebra with 2 variables x, y to the Leavitt passage for this graph. So we send 1 to the sum of the vertices here, and we send x actually to alpha plus beta, and we send y to alpha star plus beta star. Then we see the Leavitt passage here actually is isomorphic to kxy cosine the idea generated by xy minus 1. So actually for this algebra, it's graded and it's very big. It's for each component, it's infinite dimensional. So actually, after the introduction for Leavitt passages, there are many related research areas with the Leavitt passages. So for example, combinatorics and algebras area and symbolic dynamics area, K-theory, non-commutative geometry and representation theory. And actually for mathematicians working in triangulated categories, they actually relate Leavitt passage with the triangulated categories. So for Cross, actually, he started a stable derived category of an algebra, and he so that this stable, but here I will not give the definition for stable derived category. So it's just some triangulated category, and it's compactly generated. And actually, Smith and Chen and Yang, they relate this stable derived category with a derived category of Leavitt passage algebras. So actually, for in this section paper here, for Chen and Yang's paper, they use the differential graded categories as tools. So actually here, they view the Leavitt passage as differential graded algebras with trivial differential. Then inspired by this result, I considered the stable derived category and construct an explicit generator. I denoted I for the stable derived category. Actually, as this triangulated category has relation with Leavitt passage, actually I found that the differential graded and morphism algebra for this generator actually can give us back the Leavitt passage algebra. So yep.
So the Leavitt passage algebra considered as a DG algebra with trivial boundary map, right?
Yes, with the trivial differential, yes. Yeah. Yeah, so this result is actually it's in the first paper. Actually, we also have a duality version for the stable derived category. So I have also the second paper there, but there it's not much difference, but it's a duality. So actually for any graph, so around Morano Pardo reintroduced graph monoid ME for row finite graph. So row finite graph means for each vertex of this graph, there are only finite many edges starting from it. So the ME actually is generated by vertexes subject to these relations here. So for V, so if there are edges starting from V, so we put V to be the sum of U, such that U are the ranges of edges starting from V. So actually, they prove that this graph monoid give us the monoid of isomorphism classes for the finite generated projective models over Leavitt passage. So actually, around Google, they can extend the definition for ME to arbitrary graph E. So actually, actually we can have more generators here and more relations. Yeah. So here, but we will not see all these details, but we know that we can have monoid for an arbitrary graph. So actually, we have in this paper, so this is with Aran and Harriet, we actually have graded graph monoid. So here we can also for an arbitrary graph, but here we only give definition for row finite graph also. So the generators for this graded monoid is Vi. So V is any vertex, I is an integer. So we have the relation that for V, if their edges starting from V, so then Vi is the sum for this Ui plus 1. So U is also all the ranges of edges starting from V. So, but here we have, here is I plus 1. So actually for any, give us a monoid V, abelian or we say commutative monoid V, we can have a group using the group of completion. That means we can define relation x1, y1, and x2, y2 have a relation. We say that if there's element z such that x1 plus y2 plus z is y1 plus x2 plus z. So then we use the equivalence classes. We can have the v the stat v plus, and we have the induced addition here. So it's we can see it's pointwise, and actually, so we can prove that we can see that this V plus, this is a group. Yeah. So actually the inverse for XY should be YX. Right? Actually for the graded graph monoid, when we do the group completion, we have a group we denoted by K0GR. For the Leavitt passage, is called the graded crescentic group for the Leavitt passage. Actually, there's a Z action on this group. Is given by the shift function on the graded models P. So this is like n being an integer, then Pn here, this is the shift for P. That means for the gradient for Pn is given by this. So the m's component for Pn is the n plus m's component of P. So this makes this group, this graded crescentic group to be a ZXX inverse model. So actually Hazard has this conjecture that he said that this model isomorphism for this graded crescentic group for two Leavitt perceptors might be an invariant for Leavitt path algebras. So more precisely, that means suppose we have a model isomorphism for these two graded cosine groups for Leavitt path algebras. Then that means if and only if the Leavitt path algebra of E is graded Morita equivalent to LF. And furthermore, if this phi sends the LE to LF, then the conjecture says that LE is graded isomorphic to LF. So actually, Harriet proved this conjecture for a cyclic comet or polycephalic graphs. So that is like a mixture of a cyclic comet and those with petals together. So, but this conjecture now is still open. So actually for in Chen and Young's paper, they actually have this result for graphs, for finite graphs without sinks. So they say that the following statements are equivalent. So the first part is the two Leavitt path LE and LF are graded Morita equivalent. So that means the graded model categories for these two graded algebras are equivalent. And the second statement is that these two algebras are derived equivalent. So this here, they consider this Leavitt path algebra as the differential graded algebra with trivial differential.
Sorry, when you say graded Morita equivalent, do you mean that the categories are equivalent in a way that is equivariant with respect to the action of Z by a shifting?
Oh yeah, yes, it's Z graded Morita equivalent. Yeah, yes. Yeah, so so these are Z graded algebras, and this Z graded models, the model categories, they are equivalent and the respect with the shift functors.
Okay.
Yeah. And here this the derived category for this differential graded algebras, actually this is I think this is I think it's studied or it's studied I can say it's a differential grade. It's introduced using differential graded categories language. So, and the third statement is that for stable derived categories for radical square zero algebras over E and F, they are triangular equivalent. So this is the stable derived category we mentioned it before there. So this says the equivalent, they are triangular equivalent. So has the relation with this the about two contains about two statements. And actually the last statement, actually these singularity categories are equivalent. Actually the singularity category for this, it is the full subcategory for this stable derived category consisting of the compact generator, compact objects. So the third one and the fourth one are equivalent. So that is actually by the definition. Sorry, that is not the difficult part. So actually this, because singularity category actually is a part of this stable derived category. So actually in that paper, they also have, they prove that if these two Leavitt path algebras are graded Morita equivalent, then there's a model isomorphism between the graded cosine groups for these two Leavitt path algebras.
So that the fact that it's order preserving just means that it comes from an isomorphism between the the monoids, right?
Sorry, could you please repeat?
Yeah. So you say that there is an order preserving equivariant modular isomorphism. So the order preserving condition means that this isomorphism of K0 groups is induced by an isomorphism, an equivariant isomorphism of monoids.
Oh, yeah.
N-gr E and N-gr F.
Right? Yeah, you're right. It preserves the order. That means yeah, you're right. The grid graph monoid part is the positive cone for this, so it's also preserved. Yeah, you're right.
What I'm saying is it's equivalent to saying that it comes from an isomorphism of monoids, isn't it?
Yeah, yes. Yes, because
talented monoids.
So we can see this comes from the isomorphism between the graded monoids, because for that monoids it also has this Z action. So because by that definition we can have an action, and we preserve that part. Let's see. Actually, for this grid graph monoid, it is this monoid. It contains all the graded isomorphism classes for graded finite generated projective models over LG. And we can prove that this monoid is cancelative. That means for elements if x plus z is equal to y plus z, then we can cancel z. So that means we can have x is equal to z, x is equal to y, and then we can. If it's cancelative, then this from this monoid to the group completion, it is injective map. So this injective, tell us this monoid, actually it contains much information for this Leavitt passage. That means when we starting from the monoid and to the group part, to the graded crescentic group, so we do not lose any information, and we also have a one-to-one correspondence between the lattice of a graded two-sided ideas for Leavitt passage and the lattice for the graded ordered ideas for this graded crescentic group. So actually for graded ordered ideas, it's a subgroup for this graded crescentic group, so which can be write as a difference of an order idea of this monoid part.
What is the graded? The word graded. We're referring to ordered ideals of K0 gr. What does it mean there? Does it have something to do with the equivariance of reaction?
Oh yeah. For this grid, that means that means we mean that it preserves the Z action on this on this part. Yeah. So because here this group it has Z action, so if that part preserves the Z action, then we call it graded ideas for that. So actually, from the above statements, we can see that actually the graded crescentic group contains much information about the algebra structure for Leavitt passage. So this is make us like hope the conjecture for Herod might be might be true for many Leavitt path algebras. So actually for the K0 and K1 groups for Leavitt path algebras, it were first computed by Arab, Brastinger, and Kochner. And then Gap, Rees, Tomford, and Walensey extended to the Leavitt path algebras of countable graphs case. So that case, they can have infinite meters. So, but here we write down the finite graph case here. So we write down the K0 and K1, they computed it there. So first we write the agency matrix for E, so it's AE, and we write the vertices which are not sinks. That means for those vertices, there are edges starting from it. So then we list the sinks. So we have this matrix. We have B part and C part here, and then the K0 and K1 actually it's like this. K0 is co-kernel for this map X, and K1 is a direct sum, so it has two parts. So since here we have K0, K1, there are two parts, and later we want to relate the graded quadratic group for Leavitt path algebras with the K0 and K1. So we hope from the graded quadratic group for Leavitt path algebra we can have K0 and K1. So actually, we found that for the graded prime ideas of Leavitt path algebras, so it's also it also preserves the and the it also has some correspondence between the monoids part. So let's first here recall the definition for graded prime idea. So actually, we see a graded idea for Leavitt path algebra will be a prime idea if giving any graded ideas AB, AB is contained in P implies that either A is contained in P or B is contained in P.
Your ideas are always two-sided, right?
Sorry?
Your ideas are always two-sided, right?
Oh, yes, yes. Yeah, yes, it's always two-sided ideas. Yeah. Yeah, see, yeah, here I should write two-sided idea. Yeah, we denote the set of all these graded prime two-sided ideas of Leavitt path algebra by this spec LE, and GR is here. That means consider the graded case. Actually, this set has a topology. It's called Jacobson topology, and we can see the open sets. We can write on the open set for that. Actually, we observe that the lattice of graded prime two-sided ideas for Leavitt path algebra is isomorphic to the lattice of prime elements in the monoid part. Actually, we can give, we call it the order prime ideas for this lattice. So because before we know for graded two-sided ideas of Leavitt path algebras is one-to-one corresponding to graded order ideas for the graded quadratic group. So here, actually, we can, for the prime elements, we can also here know that there's a one-to-one correspondence for these prime elements. So when we have this, we can this allow us to lift the isomorphism between graded quadratic groups to a natural homomorphism between the topological spaces for the graded prime ideas. That means, so it's like this, we have this lemma here. So for EFB finite graphs, actually for row finite graphs, we also have this. So that means suppose we have the isomorphism for the graded cross-entity group here for the two Leavitt path errors LE and F and LF, then we see we have a homomorphism for these topological spaces. Yeah, so in fact, when we have this, later we can relate this graded cross-entity group with the filtered K-theory.
That's just a little question. Does this topological space, the spectrum of graded prime ideas, carry any canonical sheaf?
For canonical sheaf.
Or some sort, not necessarily of rings, you know, or something.
Oh, that I don't know. Yeah.
Okay.
Yeah, that I don't know. Yeah. So actually here we we have an exact sequence for groups for cross-entity groups for Leavitt path errors. So we actually here for E, if E is any graph, we can also have this exact sequence. But here we only write for row finite case. Yeah, because we see before, if we write for arbitrary graph case, we have more generators for that monoid. So that means when we consider this graded cross-entity group, we need also consider more generators. Yeah, but it's okay. But yeah, here we only write for row finite case. So here, so this starts from K1, and then here is K0, the graded K0, and then graded K0, then is K0. So here, this U is given as induced by the forgetful functor. So that means UVI is V actually. So for phi, actually phi is induced by this phi VI is VI plus 1 minus VI. So we can see the image of this phi VI is in the kernel of U, yeah, from the definition here. And here, this T, actually, this is the comparison for the isomorphism and this projection.
Is that the so-called Vandenberg sequence?
Oh, yeah. So you mean where from the exact sequence?
The one for a strongly graded ring relating the graded K theory with the ungraded one.
Relate the graded cross-entity group for strongly graded Leavitt pattern to non-graded one, right?
Yeah. But here, yeah, I don't know. I mean, there is such a sequence. I'm just asking whether it's the.
Yeah, so here.
Because you have the phi is the identity, or sigma minus the identity, right?
Phi is
the action of the integers minus the identity.
Oh, yeah.
And that also appears in Vandenberg's sequence.
Yeah, but here I don't know where it relates with strongly graded. Yeah, but for strongly graded case, yeah, they also have that. Yeah, it might have that. But, for sure, but but I don't know what the specific relation for with that strongly graded case. So so in the following part we talk about the filtered case theory. Actually, it's further developed by Eilers, Restov, Rees, and Shorenstein. So Actually, the sublattice for gauge invariant prime ideas and their subquotient K groups for C-star algebras can be used as an invariant. So here, these are the two papers about this filtered K theory. Actually, the first one, I think it's about maybe algebra part of a filtered K theory. The second one is about C-star algebras filtered K theory. So actually here we actually they also give the filtered K theory in the poorly algebraic setting. So the definition is exactly in the following. So we suppose K is less than M. The filtered K theory of a graded ring R actually is this collection of all these algebra K groups for graded ideas R and J of R, such that R is contained in J. So here, here we have the K groups for J over R. And we also need together consider the exact sequence for three graded ideas, I, J, K, such that I is contained in J, J is contained in P.
You must need some hypothesis so that this sequence exists, right? Because K theory does not satisfy excision, right?
You're right. You're right.
Kinds of rings.
Yeah, you're right. So as for me, I only consider for Leavitt path algebra. So it is it R has some relation that, so we have that. Yeah, you're right. You're right. So actually here this exact sequence is given by the thought exact sequence between J over R. So we have a thought exact sequence using these three ideas here.
I have a quick question. How is the grade filtered K theory defined? Like FK?
Graded K theory.
Graded filtered K theory. How is this defined?
It's that collection there, isn't it?
Oh, just the collection of.
Yeah, it's not one group. It's a collection of groups together with connecting maps.
Okay, so I wonder how is this related to big, like, Abi, Oyano, and myself, we introduced those. Sometimes we call it the quantitative K group, but we introduced those K theory for filtered C-star algebras like quite many years ago. I wonder how this is related. Of course, this is algebraic K theory. We were doing it for C-star for graded C-star algebras. I have the feeling they should be related. Other than here, you are not considering the analytic structure. It's just a comment. So.
Okay, I see. So it's that maybe here. So we consider all the graded K groups for that. Maybe. Okay. So actually, for they have this the following theorem says that if filtered K theory for Leavitt path algebras over C are the same, then the topological, then the filtered K theory for the C-star algebras are the same also. So actually, for us, we used this result, to prove to prove the result for our for the part with relation with safety equivalence. I think for Carson, Eilers, and Tomford, they described a group isomorphism from the kernel to the topological K1 for C-star algebra. And actually here, in order to have the filtered K-series for left passengers, so we want to connect the K1 with the with the kernel also. So we adapt this formula, and then we can define a map Chi1 prime. But however, we found that it's not a group homomorphism. Because we found that there are some very simple examples that this Chi1 prime is not group homomorphism. So then later we want to adjust the map so that we can have a group homomorphism to relate the kernel with K1. So then let's recall the long exact sequence for K groups. So it's like this. So it's from the it's just the first part of the long exact sequence. So from here we have the map lambda prime. It's sent to K1 of left passenger. Then we collect all these images for this element. So for each vertex V, here we collect this element 1, 1, 1, and only -1 corresponds to the component of V, and 1 corresponds to all the other components. So we know this is an element here in this group. It has image and lambda prime. We denoted it by -V1 here. And we use this element to generate a subgroup of a K1, and we denote it by DE. So then we define a K1 bar of left passenger as this K1 quotient this subgroup DE. This group we call the reduced K1 group. So when we have the reduced K1 group, we actually have this commutative diagram. So P is the canonical projection from K1 to K1 bar. And here this cassette prime is from the long exact sequence. So this actually, we have this induced cassette here. Because from that exact sequence, we can see that we have this cassette there. And then we can have a new K1. We have a K1, which is a comparison of P with K1 prime. Actually, we can prove this is a group homomorphism, and it's a section of a cassette. Because we know cassette prime is a split, so it has a section. So here, cassette also has a section. So this proposition, this is one part from result which is in the joint work with Ara and Harriet. So then we define the filtered K series, a filtered K bar series for left passenger as a collection of all these reduced groups for this J over R. And IJ are graded ideas for left passenger such that I is contained in J, and K0 bar actually is just K0. So actually we can see K1 bar is defined for left passengers. So here Q1 bar for the quotient can also be defined because this quotient is also isomorphic to a left passenger. So actually, moreover, we can, for three ideas of the left passenger, the grid ideas here, and they are natural maps from K1 bar to K1 bar for this, then to K0. So actually here it's induced by the long exact sequence of algebraic K series. So this is the definition, and then we have the main result in our paper that for row funnel graphs and E and F and the Latakia field, we suppose we have this isomorphism between the graded cosine groups for LE and LF. Then we have the same filtered K series for this LE and LF. Actually, for this proof, we use the long exact sequence from K1 to grid K0 to grid K0 to K0. So we use the grid K0 to connect the K0 and K1 together. So actually, we piece all the K0 and K1 for ideas of a Leavitt path algebras. So actually, for our results, actually we have relation with the fielded K-series for cis algebras. So actually people, let's see, we have this diagram here. So suppose for two Leavitt path algebras, they are isomorphic, they have the same grid K0. Then we see this is our theorem. We have the filtered K0 are the same. Actually, we take the field K to be the field of these complex numbers. Then we can have the filtered K series for cis algebras. They are the same also. So actually, this proof is similar as the we use the same way which they proved that for the filtered K series for cis algebra for Leavitt path algebra the same. Then the filtered K series for cis algebras are the same. And then here we know that they already have results that this filtered K series classifies the cis algebras there. So actually, so we can have the cis algebras for E and F are Morita equivalent also.
It might be worth mentioning that at least in the case, I think when E and F are essential, then this K0 group is Krieger's dimension invariant.
You're right. Yeah.
And so this isomorphism means something like shift equivalence or something. And so you're saying that there is a dynamic condition that is, I think it's shift equivalence between the two graphs. And
yeah, you're right. Yeah, you're right.
That implies Morita equivalent sister algebras, right?
Yes, shift equivalence for two final graphs. Yeah, I think without things. I think without things. Then we can. As you said, that we have the isomorphism which is invariant, and that has the graded K0 are the same. Yeah, and then apply this. Yeah,
because this was previously before your paper. I think it was only known in the irreducible case.
Yeah, you're right. So for here we can we have for the final graph without things. Yeah, for that case. Yeah, actually we hope we have filtered K series result for an arbitrary graph, but here now we only have results like along that sequence and some other, but we haven't. Yeah, it's like we are on the way, but we haven't got for an arbitrary graph case. Yeah. That's all for my talk today. Yeah, thanks very much. Yes, thanks.
Thanks a lot. So I already asked many questions. Perhaps there are further questions from the audience. Okay. Would you give me a hand, Efren? No.
Yeah, I have a question. I'm looking at that the map that you said it wasn't a group homomorphism. Would you explain further why you don't have a group homomorphism from the kernel? I think it was the kernel to K1. Because I think Carlson, I think that map, isn't it just from the long exact sequence from looking at the Toeplitz algebra to this graph C-star algebra? When you cited the Eilers, Tomford, and Carlson result?
Yeah. Let's see. So it's let me see. So it's you're asking what? Let me see.
I think it's.
Sorry, let me see.
In the opposite direction.
So it's
Yeah,
here.
Here.
Yes.
So I think it's because for topological K1, it's isomorphic to kernel part. So here, let's see.
I mean, I think you can. I had a similar map once but it was in the simple case, in the case of simple graph algebras, and you could make it. I mean, it maps generators. It's a section of the level of generators. You choose a basis. It's a section, a set theoretic section. So if you can make a group homomorphism out of it by defining it as the section, you choose a basis because it's a free module, a free abelian group. You choose a basis and define it just like that on the basis and then extend by linearity. But the point in that Huanhuan Li and her co-authors are making is that they want some canonicity, right? Not that something you need a basis. You need to choose a basis for. And I think that's what they manage.
Yeah.
Right, because you wanted to satisfy everything when you're doing these filtered K theory, and you want those LODs as canonical in some sense.
Yeah.
Or respects.
We need the functor thing for the subquotients for Leavitt passengers. So that means we need to relate the subquotients for graded ideas for Leavitt passengers. So we need a special, very special group homomorphism such that they can have many commutative diagrams between the K groups for graded ideas and K groups for the subquotients for the Leavitt passengers. It's like that. Yeah. So basically here we only adjust actually from this long Z sequence. So we cosine some images of lambda prime, but it's still in the kernel of psi prime. So actually, before here, these Chi1 primes, so we see it's group homomorphism. There are some elements when we choose different permutations, it gives us some elements here. They are not the same, but they are in the but they are in the they are in the image of lambda prime. So we cosine that part. Yeah, so it's like that.
Thank you. I have one more. It's not really a question, but more of a comment and an open question, if you don't mind me asking. And this is related to Willie's about the Schiff equivalent. So would you go back to your slides about these various implications from the, I think it's toward the end, right before thank you, I believe.
For the end?
Yeah, right there. So as Willie mentioned, the top line, when E and F are essential graphs, then that is equivalent to Schiff equivalence of the dynamical system that's associated. So, and so if we look at E and F to be irreducible graphs, then it is known that Schiff equivalence implies flow equivalence of the symbolic dynamics. And in general, that's an open question in symbolic dynamics. Schiff equivalence implies flow. And so this is more of a question for you to consider. I'm not asking for an answer because I don't think it's an easy question, is that I'm wondering if your proof allows us to say that when you have an isomorphism of the graded K0 groups, then you have this SLK web isomorphism defined by Boyle and Wang, because then that would be implies the shift spaces to be flow equivalent. So, but you know, that's my comment about, you know. So I'm maybe because if you
for flow equivalence, then you want to have you want to compare Leavitt path error, right? So
I mean, doesn't the flow part have to do with the isomorphisms or equivalence or molecular equivalency or whatever, preserving the diagonal?
Yes, that's correct. Yeah. But there's also a K-theory condition from Boyle and Wang. Basically, you have these filtered K-theory, and then the maps on K0 and K1 can be given by matrices, and they have to have the same kind of determinants. So this is what they call a SL-K web isomorphism. And so that's equivalent to flow equivalence. And so I'm just wondering here is that given your construction, do we get a K-web, this SL-K-web isomorphism from Wang and Boyle and Wang? And that would imply shift equivalence implies flow. And moreover, you would also get that the Leavitt path algebras are Morita equivalent as well, because of the fact that shift equivalent spaces, shift spaces will give Morita equivalent Leavitt path algebras. So it's something to consider.
Yeah, okay. So for so it's related to flowing. For that for flowing, that I'm not. I don't know.
I think since this diagonal preservation business was mentioned, I won't refrain from making propaganda of a paper by my student Guido Arnone, who showed that any equivariant homomorphism between K0 groups lifts to a star algebra homomorphism between the Leavitt path algebras that preserves the diagonal, and which is also so it's a star algebra, a graded star algebra homomorphism that preserves the diagonal.
So would you say that again, Willie?
So you have say you have an you have a homomorphism between K0 graded of LE and K0 graded of LF that preserves the order structure and the order unit. And did I say it is assumed to be equivariant with respect to the shift action? So suppose you have all that, then it proves that there exists a unital graded homomorphism from LE to LF that preserves the involution, the diagonal, and so that when you apply K0 gr to it, you get back the homomorphism you have. This lift, he also shows that this lift need not be an iso, even if the map of K0 groups you started with was an isomorphism. But it kind of hints towards a necessity of, that if you would have such an isomorphism, that if you will be able to prove that there is an isomorphism, that an isomorphism lifts an isomorphism of K0 graded groups lifts to a graded algebra homomorphism, then you might also be able to prove that there is one that preserves involution and the diagonal. I don't know.
So if that's the case, then that means Roosba's conjecture is actually not true then, right? Because there are ship equivalent
because of this famous Rouge. So whose counterexamples are these?
Yeah, the Kim and Russia's examples where ship equivalence is not the same as strong ship equivalence.
Yeah,
and
well, so Adam Doron gave a talk in this very seminar, the Australia-Asian node, about this paper that he has with Eilers and Carlsen, where he hinted also that he didn't think that Haskell's conjecture was true precisely because of a reason similar to that you say.
Who's your student?
Guido Arnone, Arnone. And Guido is, the Italians would say Guido.
Thank you.
Okay, you're welcome. Well, so I think I only have left to say to thank Huanhuan for her dedicated service to the community by giving a talk at 3 a.m.
Yes, thanks to everyone for your coming for this.
Oh, thank you.
Thank you.
Thanks.